Is it just a line? No, it's more than that. It is the gradient function, right? So we are given the gradient function, which happens to be a line, yes. It is actually negative, and it is a linear, right? A negative line. Cool. Now, that's the gradient function, which tells us, for example, when x is 0, the original function has a gradient of positive 6. When x is 2, the original function has a gradient of 0. Right, the y value is 0. So the original function's gradient is 0 when x equals 2. Cool. And the question asks, sketch the graph of the original function. They also tell us that it passes through the origin. Alright, so let's just have a think about the shape first. We have the derivative. It is a linear graph. When we anti-differentiate, a linear graph, for example x, the antiderivative would be x squared over 2, right, plus the integration constant. So we would expect a negative, excuse me. We would expect a negative quadratic. So just by acknowledging that this is a negative linear graph, the antiderivative will be a negative quadratic graph. So with that, is it going to look like that? Like that? We don't know, right? We need to position it based off of a few key points. But at least right now, we know the shape. Cool. So, key point to look out for on the gradient function is the x-intercept. Because on the original function, that means it will be a turning point. It will have a gradient of 0, in this case when x equals 2. So, for our quadratic, our negative quadratic, we know that the maximum must go through that dashed line. But how do we fix it into position? Well, the question told us it must go through the origin. So we can put our first point at the origin, and this dashed line, because the maximum goes there, it's actually also called the axis of symmetry, right? Because a parabola or a quadratic graph is symmetrical about the turning point, which means if we reflect this point, we would get another x-intercept at positive 4. Yeah, because it's symmetrical. And with that, we can then draw in our graph. So the maximum, I don't know, let's say we'll put it here, and we connect the x-intercepts with the maximum, connecting our curve. Alright, and put a little squiggle here if you want it to look like a face. Don't actually do that. Alright, so let's quickly summarize this. Looking at this straight line, we acknowledged it was a negative linear graph. So when we anti-differentiate, we get a negative quadratic. So we know the shape. However, we looked for the key point, which is the x-intercept on the gradient function, right? And that will correspond to the turning point on the original function, because it has a gradient of 0 at that point. We were also given that the original function passes through the origin, and then since a parabola is symmetrical about its turning point, we were able to plot the other x-intercept, which then let us connect them ensuring that the turning point goes through that dashed line. If you made your turning point a bit higher or a bit lower, that's fine, right? As long as it went through at x equals 2 and it went through both intercepts, that would be merit. However, if you only got the intercepts or you only got the turning point correct, that would be achieved. Cool. See ya.